Feed tank. So it's got that written right on here. That helps you figure out which one goes where. Pretty sure this is pump one. So that's this one. If you want to move fluid from the bottom tank over to the makeup tank to recover what was left over from the last run to get ready for the next run, you open this valve, open that valve, open this valve, make sure this valve is closed, turn the pump, and then you do that. So that kind of a procedure would need to be a lot more detailed than what I just said.
That pump?
Pump number which?
One.
Okay. All right, and we provided some rough indications here of what your flow rate to meter reading might be, but you don't know if it's the top of the ball, the middle of the ball, or the bottom of the ball. How are you going to figure that out? Calibrate it. Okay? One trick to calibrating it is you don't want to have this open when you have this open. Because what's going to happen is any liquid that's in the line is going to come back down. And then it's going to flow out at the same time this is flowing. You're going to think you've got twice as much flow as you actually have. Okay? But if you keep this closed when you're trying to feed the column, this is going to read pretty close to zero because it's closed. So you got to open the valve. Don't use this as an on-off valve. This is an adjustment valve for the flow rate control. This is a control valve. This is an on-off valve. We talked about this one already. That's how you measure your steam condensate.
Well, we have like a scale under there that's measuring that mass every time.
So there's that one. Bad news about that one is somehow one of the little discs for measuring extra weight got lost. So when you get to 15 pounds, you never run into that one. Good news is this one only holds about 17 pounds. So you just kind of catch it moving or so let's go on up. Careful about the kick of this one. And if you look inside, I think it's this particular. Oh, right here. Okay. You see this glass tube? How it goes down to this tray, and then the same glass tube just pokes through this one. Okay, that's called a downcomer. And I think we have enough liquid on this tray that we're just kind of covering the bottom of this downcomer here. That's good because it means that the vapor coming up from the tray below through the little bubble cap holes can't just go straight up the downcomer.
Okay.
But sometimes that's not the case. And when things are bubbling and gurgling along a lot, what can happen is the vapor does go up and down. If you've got vapor, because that's the path of least resistance. It's a bigger hole compared to those little bubble caps. So if it can go that way, it will go that way. And then what happens is if you've got vapor coming up the downcomer, the liquid on this tray can't go down the downcomer because it's getting blown out. And then this tray fills with liquid. And then the next tray fills with liquid. And this is called flooding. Okay?
Yep.
So that's what we don't want to see happen. We want to be aware of that and catch it before it goes too far. Good news is, with all the repairs that we've been doing, I think that we were able to avoid that in almost every situation. But it did happen to one of the teams a couple weeks ago. So it's still possible to do it.
Do you have to scrap it and kind of start over at that point, or is there a way to adjust it back?
What you can do is what I call bump the steam.
Okay.
Just turn the steam off for a second and then yell back and forth and say, "Here it goes, there she blows." Something like that.
Yeah.
And then you turn the steam right back on quick enough that you can catch this one before all the others have dumped.
Okay. Okay.
So there's a little trick to that. This valve over here is for adding DI water to the makeup tank. And so what you'll do is we'll provide a drum of methanol you want to figure out how much methanol you've got in your makeup tank to start with in order to mix up and get to about 15 to 8% is where we're headed. And then you'll be ready to run. And so you'll do a quick density measurement of what's in there, get the composition, figure out how much you need to add, load the feed tray, go to town. So you can see why if your objective is to get out of here as soon as possible, you want to come with those measurements ready to go, calculations ready to make, and assign duties so that happens quickly. These here are called feed trays. So the feed trays are 4, 7, and 10. But those are stages 5, 8, and 11 because the condenser counts as a stage. And if you want to feed this tray, you better make sure this tray is closed because the gravity comes up this way, and so if this one's open, it's going to go out here first. This is an important valve. I think it's 201. What do you think we might use that for?
Reflux? Or reboiler?
That's a reboiler.
Okay.
Okay. And so, this I'll tell you is the feed line. Okay. And so, if this valve is closed, it just goes down to the feed rotometer and it comes back up again to the feed trays. So if we want to fill the reboiler as fast as possible, we just open this latch. Okay. So when we're getting started, that would be the way to go. Another way to bump the reboiler would be to just pour in some cold feed.
Okay.
But that's a little less controlled than bumping the snake. Okay, I think unless there's any questions, we can go to the next level.
I got one on my real quick. So with any of these valves, do we want to be opening them 100% all the way, or
Nope.
is it something that we're going to be doing it
We
slow?
never open a valve all the way.
Okay.
We open it all the way and then turn it back half a turn.
Okay.
Do you understand why?
We don't want to get stuck in that position.
Exactly.
Okay.
If it's stuck closed, that makes sense, right? Because you want it not to leak, okay? But if it's all the way open and we don't know if it's stuck open and we think it's stuck closed, then we're going to start cranking on it, opening it further when it's already open. That's why we want it loose when it's open. Everybody understand that?
Mm-hmm.
Very important valve maintenance theory there. Okay. These are sampling ports, so you can measure your tray compositions here. All of them work except for 1, 3, and 5.
So these would be the composition numbers that we've seen on the Excel sheet.
Right. These, and we can measure the reboiler, like we talked about directly, and we can measure the distillate. And maybe now's a good time to go look at how we measure that. Okay.
Do you know how tall it is?
I'm thinking 20 feet.
20 feet. Okay.
I think it's 9 inches per tray,
Okay.
and 9 inches in diameter. But you should measure it. Just
Yeah.
make
Yeah.
sure.
Okay.
So
So
let's take a look at our reflux splitter. the way that it's
R6 and
working.
2.
So you see how it's 6 seconds down and 1,000, 2,000.
Yeah, 6 and 2.
Okay. So if I wanted to sample my distillate composition, where do you think it'd be a good valve for doing that?
Maybe this guy right here?
Yep, that's the guy right there. Okay. So you'll see that you get a buildup of liquid in here, but if you want the distillate composition at the moment of sampling, you want to drain that first and then collect your sample fresh.
Okay.
Okay? And it has this little dip tube in it so that vapor can't go back up the column. So, we've talked about how important it is to measure the condenser duty. How are we going to measure the condenser duty? And notice that the condenser has coils.
Mm-hmm.
So would we do the United of the feed again?
You will need to do that,
Okay.
but not to measure the condenser duty, but to measure the heat transfer coefficient.
Oh, okay.
Just like with the reboiler,
Okay.
you can
This is a
estimate
cold
the area.
water.
You can estimate that
Yeah.
cooling water.
Yeah, going into the coils. The evaporated methanol around it
Temperature in
dropping
the condenser
down.
from this is another very good
And that's the
thermocouple.
Okay.
Okay.
content.
So you know your
Water
ability
content.
across the heat transfer.
This is the
Mhm.
condenser and this measures
Oh,
the
you've got to get your cube
of
somewhere.
water
Right.
going into the condenser.
Alright,
Coming
You
so-
know
out of
everything there
condenser.
except for pneumatic.
If we can measure
Okay.
the methanol condensed versus the water flow rate, then we can measure the duty.
Actually, you can do it the way that you expect you can
Put the airlines
do
on there
it
and say where
in
they
two
connect
different ways.
No.
Whatnot? No. Okay.
So
just
what's
indicate
happening
it's
with your condenser?
Okay.
You're condensing your methanol or whatever, you're
Mhm.
getting it from here, right?
Yeah.
So how we can do that? Do we use that?
Are we supposed to hand draw that, or
or
make it a ChemCAD, or is it?
Mass.
Um,
So
you know,
mass, what do you
if
might
you wanna
measure?
just
So you measure
add,
the mass and
you
then
know,
which
things
formula
for
you're gonna use.
indicating those controllers and pressures and indicators and stuff like that.
Mass, density, change in temperature. No.
Use a circle to
Changing.
It's not
What is the process that's
yeah,
happening
temperature.
in the
Yeah,
condenser?
it is temperature.
So how are we going to measure the condenser duty?
Yeah. Well, the one way that I had said was you can measure your flow rate here
Okay.
of your cold water, and then you also have your sample of methanol, how much you're condensing.
Okay.
So you have the how much cold water at a temperature defined, you know it takes to condense that much methanol. But
So the methanol is condensing at 3 degrees Celsius?
no,
Because we measured the cooling waters at 3 degrees Celsius.
yeah.
So I'm not
But
gonna-
there's change in temperature.
This thermocouple
Yeah.
measures the temperature of cooling water coming
Yeah.
going in, and this
Yes.
measures the temperature of cooling water coming
Yeah.
out.
Yeah, change in
We
temperature
looked at the
and
dial
flow.
number
Yeah.
15 and 16.
And then what does this guy
The-
here measures? If these blue lines are for condenser.
The flow of the cold water.
So some indication of the flow rate, right? So you have the flow rate, you know the temperatures going in and water going in and coming out of the
So which of those
condenser.
3 equations do you want to use?
CV dot D.
Yeah.
What's the CP?
Specifically, we have to look that up.
Whatever for a number. You should know this one.
Of water as a liquid. 4.81.
4.184.
4.184.
4.2.
So you measure, you said one way of doing it. There is another way
Yeah,
of doing
joules
it.
And you
per-
started to say it, but you mixed up.
With
Yeah.
this part.
Yeah.
So you said condensate coming out of it. You told me to measure the mass of condensate.
Yeah, you
So
could
now-
also measure that one.
So I have the mass of condensate.
What the HVAC times mass?
Yeah.
H, yeah.
And if
Yeah.
it's a boiling water experiment, then what HVAC do we use?
Or just meet the vaporization water.
Okay. And if it's a methanol distillation, what HVAC do we use?
Vaporization methanol.
That's right. Okay. But don't use the other one for the other one.
Yeah, that would
Because that has been done.
Very well.
More than once, I imagine.
Okay, but when measuring this mass, you need to do reflux, right? So what you're interested in is the total mass, not just the mass that comes out of here. So you have to consider your reflux ratio when you're going to calculate your condenser VOD, measuring this mass, because what you need in that formula is the total mass that condensate. This way you're only getting part of the mass, right?
Okay, so we're currently at a 6-to-2 reflux ratio, right? So I collect 10 cc's here. What do I multiply that by?
3.
Figure out the total condensate flow rate.
3.
I've heard 3 and I've heard 4.
When you multiply it by the mass of condensate, or whatever was in there,
The 10 multiplied by 1. Should I state the problem again?
yeah.
Yeah,
Okay.
so there you go.
So I stuck my graduated cylinder in here and I measured 10 cc's
In 2 seconds.
in however many, yeah, some seconds. Okay. Now I have to multiply that by something to figure out what's the total amount of condensate. Do I multiply by 1?
By 3.
By
3?
Would it be by 4? Because
By the ratio of 6 to 2.
But don't we want the total? So the
Oh,
total
yeah,
would
so
be-
you add 1, yeah.
Yeah, so you
4,
do-
yeah.
Yeah.
You're right. I didn't think, yeah, add 1.
8 over.
Is it 3 or is it 4?
so I'm shaking her head.
I'm going to go with
Yes,
4.
so-
I'm going with 4 because he's, yeah, I didn't think that I
Stick to your
add with what you have. Yeah, you're right.
It's a little
Yeah.
scary, but.
Yeah. Because 6 and 3 in one, 1 in the other.
Yeah.
Okay. So yeah, 4 would be the right one. Yeah. Okay. So, but I like the reasoning over there better. Okay. So I think we're done.
Okay.
Any questions? It's the feed tank. As you're filling it, you should be able to see the level. Right?
Mhm.
It's now in below HO. If you look at that black line, there is now.
Okay.
There's a couple HOs on there.
No, not the first
The
one.
thick one.
With the,
Yeah.
between the two, you
Yeah.
see that level.
So on Tuesday, we're supposed to turn in PID, procedure, and then safety. So,
Plan of investigation, I think.
okay.
Yeah.
Do we turn in one as a team, or do we each turn our own?
Yeah, the general things can be team and the critical group.
Okay. Okay.
Are there any, like all the steam lines labeled to correct my son here?
Alright, so-
Is there anything to look out for?
Yeah, don't grab the steam.
Yeah, okay.
All right.
But they say like steam right on most of that stuff. Or...
Oh yeah, well you see them. See the little green label that says air.
Oh yeah, down there. Okay.
And then the white one, I guess,
Alright.
is steam one.
The blue one is the safest.
The blue one is the cold cooling water.
3 degrees. All right.
Yeah, we will cover those up eventually, but I mean, there's always going to be hot surfaces.
Right, yeah.
So
Okay.
you just have to be a little alert.
Will this be updated when
for?
Probably.
Depends if we choose to empty it, right?
Yeah. No, we should have it empty so that basically so that you can just put everything in the makeup tank quickly and get it up to the composition. Another rotometer. So, are we doing rotometers? Yeah.
Calibrate.
We never trust anything.
We've done quite a bit of rotometer calibration regressions in lecture, so
That's good.
That's why.
One more skill. That's why the distillation column is so much fun. You get to use all your skills. Heat transfer, mass transfer, rotometer calibration, density calibration, maybe even a little GC before.
okay, so that's just an electromagnetic control.
I know areas,
I
but
think so, yes.
Yeah.
in the R&R, when it says
Yeah,
preliminary
you have
report,
that's
that's
the-
positive and
Yeah.
negative,
quiz.
Yep.
Okay.
Yeah. Well, and
and
the
off,
investigation.
on, or well,
Yeah.
this is probably off. And that's on, less power that way.
Is this stuff just like a label?
Well, that's what you get from the miraculous.
Oh, that's definitely on.
The installation starts.
And that's off. Yeah.
Yeah, well, in order to hold it on the top, they used a certain kind of tape that looks a lot like that. Like AKA duct tape.
Okay.
So, yeah, that's duct tape engineering right there.
NASA.
We could probably clean it off with the right solvent if you were strong enough, patient enough.
Somebody has time to do this stuff.
But yeah, then we'd just mess it up.
So is this just another column that no longer gets used?
Yeah, originally when they built this back in the 70s, they thought that you could see that this is designed with a kind of a swivel in it,
Mm-hmm.
so that you could just switch it over to there and you could do some experiments with the pack column and compare how a pack column operates similarly or differently from the tray column.
And you have multiple pack columns.
Well, that's because with that pack column, and it happens that when it's very narrow like that, much more narrow than this one,
Mhm.
smaller diameter, what happens is the liquid has a tendency to just go to the path of least resistance. And it packs the least around the side, and so the liquid just goes down the side, it doesn't go down the middle, and what you conclude from that is pack columns don't work worth anything. But really, they do work. But what you need is a system more like this, where you see you've got a very sophisticated distributor plate, and then you've got a dripping section, and then you've got another redistributor plate, and then another pack column section. Because if you just let it go to the walls, then you tend to go there and stay there. So you need to collect it and redistribute it from stations.
So another 15 years, one of those might work.
This one actually works. We're just not using it right now. What it does is, and you want to be careful with this, you want to leave that valve where it is, because if you change it, you'll be sending liquid down this column, and liquid will just be pouring out on the floor. So
Okay.
we prefer that not to happen.
Should we include these on the PNID, or do you just mention it goes to the other
Just mention
columns?
that valve goes off to somewhere else, to blah, 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 to absorption column,
Okay.
and be sure that it's in the right position. So what we can do is mix 1 molar sodium hydroxide solution and pour that in here and drip it down the column. And then we blow air that's been doped with CO2, and it reacts and it makes baking soda. So the white powder that you see in places, that's actually baking soda. And then we can use that approach to equilibrium or conversion. We can measure the CO2 coming out, measure the concentration of the sodium hydroxide going in and coming out. From that, we can figure out our chemical transfer. And this one actually mimics real life.
Oh, it does, okay.
This is a fairly sophisticated distributor plate, and this whole apparatus really was designed by a guy out at what used to be called Norton. It's now called St. Gobain in Stowe. If you look in Perry's handbook for all of the figures where they show you how to get Murphy efficiencies and what a tray, what a bubble cap tray looks like, what a pack column looks like, how to get height of the tray for me. All of those graphs came from Norton. It's very cool. Unfortunately, they don't exist in St. Gobain.
All right, so we better get to drawing.
Yeah, right.